Hi, everyone. Thank you so much for joining me here today for Privacy Shift Left, a machine-assisted threat modeling approach. My name is Kristen, and this project was a joint venture with my manager on my last rotation, Vaibhav Garg. We're both coming to you from Comcast Cable. Let's jump in with an exploration of what it means to shift security and privacy left. If it's in the name of the talk, we should probably understand it before we go ahead and go on with the rest of the talk. So what you're looking at here, this blue diagram at the top, is representation of the traditional software development process. We start out on the left with requirements engineering. This is the process of talking to our customers and understanding what their needs are, as well as any constraints that we have when fulfilling those needs. We take this conversation that we have with the customer and we attempt to turn it into technical requirements, functional and non-functional requirements that dictate how our system will be built and perform. We use those requirements then to guide our development of an architecture design. The architecture design should be a high-level description of what our system looks like. What are the technical components in the system and how do they talk to one another? What are the communication paths and what are the protocols in place? This architecture design then dictates what we develop. So that next phase of software development is actually building out that architecture. It's a long process of coding and debugging and so on until we've built out all of the components that fulfill that architecture and hook them all up to one another. The next step is testing, but it's important to take a step back here and understand that this is not truly a linear process. This is actually a process that's quite cyclical and that involves some interplay between the phases that we see here. They're not quite so cut and dry separate. When we're testing, we might test at a unit test level or all the way up at a system test level. So this is not to say that we write all of our code and then hand it off to be tested, because that would not be very practical. But this diagram is a good way of understanding what the sequential steps are to get from nothing to complete system. So during that testing phase, we validate. We make sure that the code does what we expect it to do. Then we hand over our finished product to the customer when we deploy it. And finally, we listen to customer bug reports or feature requests during this maintenance phase, But security and privacy, we didn't really mention them here. Traditionally, they fit somewhere in between testing and deployment. We build out our entire application, we validate that its functionality works, and then we say, wait, are there any problems with the security of this application, or is my customer's data actually being protected the way it's supposed to be? And then we go ahead and we come up with solutions and we retrofit those solutions to the application or to the system. Best practice dictates that that's not actually what we should be doing. What we really want to do is take security and privacy and move them all the way to the beginning of that software development lifecycle. We want to have conversations about security and privacy with our customers during the requirements engineering phase, and then carry those considerations with us all the way through maintenance. So security and privacy need to be moved to the left. How do we go about doing that, though? Threat modeling is one way that we can start to introduce security and privacy earlier in the software development process. Threat modeling is a way of looking at the architecture of a system and trying to understand what the potential security and privacy flaws are before they've actually occurred, before they've ideally even been built into the system. Threat modeling works as follows. We start out with data flow diagram creation. We ask the application or system owners to put together a representation of the technical components, that make up a system, as well as the data assets that are stored and passed around in that system. That representation is then handed over to a threat modeling architect. The threat modeling architect goes about analyzing the data flow diagram. They look for any problem areas that they might be familiar with thanks to previous threat models and thanks to knowledge of common threats. They highlight these problem areas and they come up with a list of questions, perhaps, that they want to bring to the application team to get a better understanding of what protections they might have in place to prevent those threats. Then we transition to the threat modeling workshop. This is a conversation between the threat modeling architects and the application team. Any stakeholders who might have information relevant to surfacing up threats are brought to this conversation such that we can get all the context possible or all the context needed to understand whether or not a threat is present. By the end of this process, ideally, the threat modeling architect has been able to put together a list of all of the threats that they've discovered to be present and can then hand that over to the application team for remediation. Ideally, these threats are prioritized for remediation in order of risk. So whatever threat introduces the most risk to the system should be addressed first. This is the ideal workflow of a threat modeling process, and it's quite often aided by the structure that might be lended by a threat modeling framework. There are a number of different frameworks out there. So we're looking at 2 here on the screen right now, but that's not to say that there aren't more. But one of the most common frameworks for security threat modeling is called STRIDE. STRIDE is an acronym for 6 key security threat categories that we see on the screen here, and then a number of security threats fall within each of these categories. So these are meant as a guideline or a quick way to remember, a sort of mnemonic to remember what are some of the key areas that we need to pay attention to. Similarly, as was discussed at a previous PEPR conference, Linden is a privacy threat modeling framework. Linden identifies 7 key privacy threat categories, under which for each category, there are a number of common privacy threats that fall. So once again, we can rely on something like Linden to guide our conversation about common violations of users' privacy rights or common violations of data handling that result in privacy threats. So threat modeling sounds like a promising way to introduce discussion of security and privacy earlier in the development lifecycle, such that we don't end up having to retrofit solutions later on. But of course, there are going to be some problems that occur, or really some challenges that we need to overcome. These main challenges for us are time and resource constraints. Time constraints are fairly straightforward. We're asking someone to give up their time to participate in a threat modeling workshop. We're asking the architect to give up their time to analyze information prior to the threat modeling workshop. That information that's going to be analyzed was someone had to put all of that together from the application side prior to that. And during the threat modeling workshop itself, we often take anywhere from half a day to a full day. That's a lot of time to take away from other tasks that you might be involved in, especially if you're a developer who has other tickets to fill. The other main challenge is resource constraints. Within any given company, you may only have 1, 2, 3, N thorough threat modeling architects that know how to conduct a thorough threat model. There are only ever going to be so many people who are skilled in one particular task, and we need to make sure that we're able to roll out threat modeling at scale. But if we don't have the right number of threat modeling architects to perform all of the threat models that are needed in our organization, then that's going to fail. So how can we actually help mitigate some of these issues? That's where we think machine-assisted threat modeling might come into play. Machine-assisted is not the same as automated. We're not saying that we want a robot or a computer to take the place of the threat modeling architect. Rather, we want the machine to assist the threat modeling architect. So imagine you hand an input that has a description of your system to be threat modeled to the computer. The computer takes a look at that input and parses it and comes up with a list of threats that it believes to be present, a suggested list of threats. That suggested list of threats is then passed over to the threat modeling architect, who can use that as a guideline to try and focus their conversation during the threat modeling workshop. So once again, we're not taking away the agency of the threat modeling architect, but we're hoping to help save them time. They might see that there's a common threat that they hadn't really thought of, or they might see that there's a threat that they believe the machine to have missed, and they said, oh, this is a common threat in this domain. I wonder why it's not here. Maybe it's not actually present. I should dig into that more during the workshop. So the machine is meant to guide the threat modeling architects. But the question then becomes, if we need a tool to help us with machine-assisted threat modeling, how do we pick a tool? This is where we really dove into some research here. We put together a list of inclusion criteria for our tools. We first said that the tool had to be open source. It had to be able to produce a threat report. The repo for the tool had to consist of, or had to contain commits from less than or equal to a year ago. And finally, the tool should be able to be applied to any type of system. With these criteria in mind, we then began to conduct some simple internet searches, and we used just keywords like machine-assisted threat modeling tools or threat modeling tools. With this in mind, we then transitioned to defining some evaluation criteria. So once we had a list of tools, we wanted to be able to compare them to one another by looking at certain factors. The factors that we chose to evaluate are as follows. The first is complexity of logic. So how nuanced is the logic that we can use to detect whether or not a threat is present? Does the system say, I see component A connected to component B by protocol C, so automatically there's a threat? Or does the system say, I see components A and B connected by protocol C, but I also see that protection D is in place, so therefore I know there's no threat. So can we make those more complex decisions using this tool? That's one of the main factors that we wanted to consider. Next was amenability to custom threats. Every tool is going to natively support some number of threats and some type and scope of threats, but what if we want to apply that tool, but there are threats that exist outside of that native library that we want to consider? What if our application domain doesn't necessarily line up exactly with the domain of the threats covered by a particular tool? Can we write logic in, or can we use a UI somehow to introduce our own threats to be detected by the tool? Third was operational usability. Here we turn from the tool itself to the use of the tool. For anyone who's going to be interacting with the tool, whether they're providing input or processing and receiving output, how difficult is it for them to get onboarded to the tool? How difficult is it for them to use it on a daily basis? If the difficulty outweighs the results, the value of the results that the tool is producing, then we didn't really solve any problems in the first place. Next is security functionality. So can we successfully detect security threats using this tool? And if we can, are we able to classify them as needed using any given framework? And finally, extensibility for privacy. Threat modeling is traditionally focused on security. It's only up and coming now in the world of privacy. So a number of tools don't necessarily include privacy threats natively in their threat libraries. So do we have the capability to introduce detection of privacy threats, or is there actually native support of it if that does occur somewhere in any given tool? So really, do we have the capability to ensure that privacy threats can be detected in some way? With these evaluation criteria, we then went ahead and compared each of the tools that we found when we did those internet searches before. The 6 tools that we analyzed are listed up at the top of the screen, and then the factors that we analyzed are listed along the side of the screen in this chart. The numbers that you see here are the results that we found for our threat modeling use case. This is not to say, right, that Keras with a score of -4 is the worst threat modeling tool, and this is not to say that Fragile with a score of +4 is the best threat modeling tool. Really, the best or worst threat modeling tool depends on your use case at your organization. So there's no one best or worst tool across the world or across the planet, et cetera, et cetera. So really, what we want to understand here is the process that we took to get to this point, right? We took those steps of defining inclusion criteria, defining evaluation criteria, and then we got to this point in time. What we can discuss here, and what is interesting here, rather than a prescription about which tools are useful, is which factors really became important when we were looking at privacy threats specifically. One of these was complexity of logic. A privacy threat doesn't always take the same shape as a traditional security threat. Security threats often manifest themselves as a hacker committing an act on a system, right? So there's a person doing something to a machine. Privacy threats don't always look like that. Sometimes a privacy threat is, did the company provide the notice to the user that their data is going to be used? Or did the company give the user the opportunity to consent to their usage of data in a certain way? So all of a sudden, it's not necessarily so cut and dry. We don't always have the same action happening to the same type of system. So are we able to detect more complex threats that don't necessarily take the shape of the traditional type of threats that threat modeling tools have looked at? And then one of the other important factors that we found was amenability to custom threats. As we said, security threat modeling has been going on for years and years and years. Privacy threat modeling is new. So if we don't have native support for privacy threats, we need to be able to introduce our own privacy threats. So that ability to introduce new threats was one of the key factors to making a tool useful, or for a tool making itself useful for privacy threat modeling. Now, if you want to conduct privacy threat modeling using any of these tools, and even using those custom threats, it's important to have a good understanding of what threats you're hoping to detect with the tool. For us, that took the shape or took the form of defining a privacy threat library. These are some of the sources that we refer to when we were hoping to shape that library: Lind & Go, the OWASP Top 10, and legal and regulatory. Let's talk a little bit about Lind & Go. We've already talked about Linden. Linden is a privacy threat modeling framework. It identifies 7 key privacy threat categories. Lind & Go is a practical implementation of the Linden framework. There's a Lind & Go deck of cards in which each of the categories is represented by a series of colored cards where each category is delineated by color. And then within each category of cards, we have one card for each of the types of common threats that falls within that category. If we go through that deck of cards, we're able to pick out which threats we believe to be relevant to our particular organization, domain, or even specific application. So this is one good way of finding common privacy threats that you might want to include in your library. Another source of common privacy threats is the OWASP Top 10. OWASP is the Open Web Application Security Project. You might be familiar with their list of top 10 security threats. They also produce a list of top 10 privacy threats. So this can be another good reference point of a sort of vetted and compiled list of common privacy threats that you might want to consider. And then finally, we have legal and regulatory. Depending on your location, there are different regulations that are going to apply. So we might think of the CCPA, the GDPR, et cetera, et cetera. And these are important, right? Each of these legal regulations puts forth certain customer or user rights that we need to take into account when handling user data. So it's important to turn to these sources based on our location and identify what rights the user has that we need to ensure that we're actually validating and protecting in our use of their data in our application. So finally, now that we understand the process of looking at machine-assisted threat modeling tools, looking at where we can build how we can build a privacy threat library, how can we actually see how this looks in real life? Let's take a look at a quick demo of turning a privacy threat from one of these library sources into code for one of the tools that we looked at called Fragile. This is the process that we're going to follow. First, we're going to select a threat. Then we're going to translate that threat into logic. And finally, we'll translate that logic into code. Starting with threat selection, we're going to pull, for example, a threat from the OWASP top 10. This threat is called operator-sided data leakage. Operator-sided data leakage is defined as the failure to prevent the leakage of any information containing or related to user data or the data itself to any unauthorized party, resulting in loss of data confidentiality, introduced either due to intentional malicious breach or unintentional mistake, caused by insufficient access management controls, insecure storage, duplication of data, or a lack of awareness. What we're really concerned with here is that caused by clause. Those three first causes, insufficient access management controls, insecure storage, and duplication of data, are technical causes. If we see any of those conditions manifesting themselves in a system, we might want to raise a red flag and say, hey, threat modeling architect, you should look out for operator-sided data leakage. Unfortunately, lack of awareness is a human condition that we probably can't account for in terms of just a technical system description. But what we can do is turn this threat into logic now. So we've created flowcharts that represent each of those three causes: insufficient access management controls, insecure storage, and data duplication. I'm going to go ahead and walk through the flowchart for insecure storage for the sake of time because it's the shortest. Each of the circular nodes represent a starting or ending point. Each of the rectangular nodes represent an assignment or process, and each of the diamond nodes represent a decision. So we start out and we create this empty list of all technical assets inside trust boundaries, where a trust boundary is some form of protection, some form of authentication or authorization that sits around some technical resources. So we create an empty list, and then we look at every single trust boundary in our system, and we get a list of all of the technical components that sit behind that trust boundary or that are protected by it. So we get a list of all of the protected components, and then we end up looking at, are there more technical assets to process? If there are, then we want to keep going. And we asked, is the current technical asset in scope, or is it a data store? So do we care about this technical asset right now for the scope of this analysis? And is it a data store? If it is, and if we do care about it, then we keep processing. If it's not, then we keep going. But if it is of consideration, if it is a data store to look at, then we look at, is this current technical asset inside the list of all technical assets inside trust boundaries? So essentially what we're asking here is this data store protected, or is our storage completely insecure, right? So if the data store is protected, then we jump back up to the top of this flowchart and we have no problem. If it's not, if we have an unprotected data store, then we have insecure storage in our system. So we create a new risk. And then we do this for every single technical asset. We keep looping until we finish all of them. And then finally, we return an array of risks. So you can see here that we translated that verbal description of a cause of this threat into logic. What we can finally do is turn that into code. So this is some Golang code that can be used by Fragile to detect whether insecure storage is present in a system. First, we create that empty list of all technical assets inside trust boundaries, and then we populate it with all the technical assets that do sit behind trust boundaries. Then we parse through all of the technical assets. We check if they're out of scope or not a data store. If they are, we just keep going. We jump back up to the top of this for loop. However, if not, we keep going and we say, if this technical asset is not sitting behind a trust boundary, then we have a risk. We go ahead and we create a risk and we append it to our list of risks. And finally, we return that risk. So hopefully this demonstration has shown you just how easy it is to turn a threat, a verbal description of a threat, into actual code and use it for processing and detecting a threat. Thank you so much for listening, and I encourage you to ask questions and reach out to us if you have any further questions or would like to discuss more. Have a great day.